Hey everyone, in this video I want to talk about what's called the beta oxidation of fatty acids. This is the degradative process where fatty acid chains can be broken down into small 2-carbon fragments. So basically the degradation of fatty acids produces units of acetyl-CoA, so 2-carbon fragments. And along the way some NADH and some FADH2 are going to be produced. These processes called beta oxidation, these are the catabolic processes to break down fatty acids. This occurs in the mitochondrial matrix. And basically when fats or lipids, such as triacylglycerides, so these would be TAGs, are absorbed through the diet, from the diet through the digestive tract, an enzyme called lipase will basically cleave these esters to release the free fatty acids, and those free fatty acids then go through beta oxidation so that energy can be produced. All right, so the very first steps of beta oxidation are going to involve essentially abstracting 2 protons that are next door to the acetyl-CoA linked fatty acid. So in the initial metabolism of fatty acids, you would have a free carboxylic acid. Coenzyme A is going to be linked onto a fatty acid chain, and it turns out that each time that happens, it costs the cell approximately 2 ATP. So there's a little bit of energy investment to get the fatty acid chain to this stage. I'm just mentioning that because at the end of this discussion, we're going to keep track of how many ATP ultimately are made. All right, so the very first step is that in order to cleave this molecule, which has multiple carbons extending out here, so we could have a long hydrocarbon chain, we're going to end up, or the cell is going to end up oxidizing this carbon number 2. And so when we're looking at this, this would be called the alpha carbon, and this would be called the beta carbon. So the one that's next door to the carbonyl is called the alpha, second one's beta. And since this process is again called beta oxidation, this is the carbon we're going to be oxidizing. So the very first step is we're going to abstract 2 hydrogens at the same time. This is a dehydrogenation reaction, and this is catalyzed by acetyl-CoA dehydrogenase. And actually that should be acyl-CoA, not acetyl-CoA. Sorry about that. That's just called acyl-CoA, because this type of molecule is called an acyl unit and it's attached to a CoA. So this enzyme is going to take FAD, cofactor FAD, and create FADH2. And it's actually the 2 hydrogens that are going to be removed. There's one from the alpha and one from the beta carbon, so we're going to just put a box around those. So the FAD molecule is getting reduced. The 2 hydrogens are going on to here, and this molecule is now becoming oxidized. So this is considered an oxidation. And again, this would be the alpha carbon, and this would be the beta. Now the rationale for doing that is that this now introduces a functional group that is fairly reactive. So the next reaction is the addition of water through a hydration reaction, where we're now going to add H and OH across that double bond, again oxidizing the beta position. So we've put an OH group on there. And the name of that enzyme is enoyl-CoA hydratase. So that's the enzyme name. And let me just put a cloud box around this name too. That's the enzyme name there. So essentially what we've done in this first couple reactions of the beta oxidation pathway is we've taken a fairly unreactive hydrocarbon chain, introduced a double bond, and now done a hydration reaction to add an OH group on the beta position. So the next reaction in this pathway is now going to be the oxidation of that into a ketone. Okay, so we're taking now, again, the beta position, This is the alpha. This is the beta. And this is an oxidation. So here we're going from a secondary alcohol to a ketone. And this reaction should look familiar to you. This is a reaction that's going to involve the use of NAD, the NAD cofactor. So in this reaction, NAD plus is going to be converted to NADH. And the name of this one's kind of long. It's called hydroxyacyl-CoA dehydrogenase. The names of these enzymes aren't nearly as important, I guess, to memorize per se, as say many of the enzymes in glycolysis, but they do help you see kind of what's going on here. So again, we're taking the oxygen, or the alcohol oxygen, and this is becoming oxidized. Next comes sort of the critical step in the beta oxidation pathway. Another molecule of CoA, which I'll draw out here, which has an SH group on it. So this is just coenzyme A. This is going to react specifically at this carbon right here at the beta position. And it's going to then break the bond between the alpha and the beta carbon. And what that will do, it will create this 2-carbon fragment now, which will become acetyl-CoA, and another acyl-CoA unit that's been shortened now by 2 carbons. So this CoA, once it's attached here at the beta position, it's going to be just like the one above, but it's now going to be shortened by 2 carbons. So we would now get okay, this part right here is now becoming this, and coming out of this now, we're going to now get acetyl-CoA as a byproduct. So this would represent what's called one turn of beta oxidation. And in one turn of beta oxidation, or one round of beta oxidation, if you want to call it that, essentially you're chopping down the original acyl-CoA unit by these 2 carbons. And along the way, you're making an FADH2, and you're also making an NADH. So let's just put a box around those, because those ultimately are going to become very important in terms of ATP production. One last thing I'll just mention, the enzyme that catalyzes this critical reaction, this cleavage by this thiol, is called thiolase. All right, so this, again, is called the process of beta oxidation. This would be considered one round or one turn. Now what can happen is this can now go through successive turns. So this is now going to go right here. So we'll call it successive turns of beta oxidation. And so this molecule now can come right here. The alpha carbon and the next beta carbon would be oxidized to make a double bond. It would go through this again. And then depending on how long this R group is, that ultimately is going to dictate how many turns of the citric acid cycle you'd end up doing. I'll summarize that in the next section. So briefly, let me just go through how you would calculate the rounds or turns of beta oxidation that a particular fatty acid chain would require. So if we were looking at a sample of stearic acid is a fatty acid that has 18 carbons, we would have to do the following. So we would need 8 rounds of beta oxidation. All right, and this ultimately would produce 9 acetyl-CoAs. Okay, so the way that you figure out the number of rounds, so figure the number of rounds, take the number of carbons minus 2 divided by 2. So in this case, we just plug in 18 minus 2, and then divide that by 2, which equals 16 over 2, which is 8. The reason you don't need 9 rounds is because that last round of beta oxidation is ultimately going to produce 2 acetyl-CoA units. So you only have to go through 8 rounds for a C18 compound. For the number of acetyl-CoA units, all you would do is just take the number of carbons and divide that by 2, and that gives you 9. So that's how you would calculate ultimately how many turns or rounds of beta oxidation you do. So for another example, if you were looking at a C10 fatty acid chain, okay, let's just go through the calculation real quick. For the number of acetyl-CoA units, you just take 10 divided by 2. That means I would get 5 acetyl-CoAs. And then to calculate the number of rounds, I would take 10 minus 2 divided by 2 equals 8 divided by 2 equals 4 rounds of beta ox. So that's how you would calculate that. And then ultimately, if we, again, just summarize, each round of beta oxidation, as we mentioned before, is going to produce an acetyl-CoA unit, an NADH, and an FADH2. All right, so lastly, what I'd like to do is just go through how you'd calculate now how many ATP a particular fatty acid might give, assuming that we're under optimal cell conditions. So let's just look at an example. Let's say we had a fatty acid chain that had 12 carbons. So first off, what you do is you need to figure out how many rounds of beta oxidation are going to occur. And so we would apply the same formula. We'd take 12 minus 2 divided by 2. Ends up giving us 5 rounds of beta oxidation. Okay. Now, this compound ultimately is going to give rise to 6 acetyl-CoA units. All right, so don't forget that, but we're only going to be going through 5 rounds. So what that means is that this would then generate 5 FADH2s. It would then generate 5 NADHs. And then we're going to just put here the 6 acetyl-CoAs that are generated from the total degradation of this. Now, if you recall, when we talked about oxidative phosphorylation, each of the NADHs and FADH2s that are in the matrix, and again, this whole process is occurring in the matrix, those are each going to give rise to a certain number of ATP through enzymatic coupling of the proton gradient that's generated, and then ultimately ATP synthesis. So recall that each FADH2 gives rise to approximately 1.5 ATP, whereas each NADH gives rise to about 2.5 ATP. So if I'm going to summarize now my ATP yield, okay, each of, or all 5 of these FADH2s are going to give rise to 7.5 ATP. These will give rise to 12.5. And then my 6 acetyl-CoA units, now when they go through the complete process of the Krebs cycle, okay, let's just summarize that. These acetyl-CoAs can then enter into the Krebs. They're going to give a total of, let's see, 3 times 6 NADH. Okay, again, because I'm doing 6 rounds of Krebs cycle, and each round gives 3 NADH. We'll get 2 times 6 FADH2s, and then 1 times 6 GTP/ATP. All right, and so each of these now, I need to multiply the NADH by 2.5 and the FADH2 by 1.5. So these now are going to give some additional ATP. This is where you really start to rack up a lot of ATP from this process. We get 45 here, 9 here. Let's see, is that right? 9, 10. Oh, you know what? I had a mistake here. This should only be 1. Each round of Krebs only gives 1 FADH2. I knew something was wrong. 9, and then this one would be 6. So if you total up the entire number of ATP that are generated from just a C12 fatty acid going through all of its beta oxidation, and then all of those components being degraded ultimately by either the Krebs cycle and then donating electrons to the electron transport chain, we would get 78 ATP. So that's a considerable amount of energy from a fairly small molecule. All right, so I hope that helps in terms of summarizing now how you would calculate the total number of ATP. What I'd recommend is you do for practice, the C16, which is called palmitate. Okay. Oh, you know what? When I added this up, I did one thing incorrectly. This is actually 80 ATP, but you may recall back at the very beginning of this lecture or this discussion, I mentioned that that initial activation of the fatty acid unit joining with the CoA actually cost 2 ATP. This is for the activation step. That's what gives rise to 78. So when you're calculating these, don't forget to, once you tally up your total number, subtract off the 2 ATP required for initial activation to CoA, and that'll give you the final number of ATP. All right, so I hope that helps with everything for beta oxidation, and I wish you all good luck.